Yeah, we were discussing about the CDMA system based on IS-95, right? In the previous class, I think I was discussing about the forward link, if I am correct. Is it that? Yes, I remembered. Anybody? I said I was discussing about CDMA system based on IS-95. In that, I said there are forward link and what is a reverse link. I was discussing about the block diagram of forward link, if I am correct. So, is it possible to confirm from your end, any one of you? Remembered anything? Yes, if you have remembered, definitely you will say yes, what you are saying is right. Otherwise, you will be silent only. Hope people are not sleeping. Hello. Yes, my network is there. I think I hope I with
Yes,
you
sir.
people.
Yes, sir.
Yeah. So, okay, so I was discussing about, as I said, the CDMA based IS CDMA system based on IS-95. Okay. Yeah. I think I've gone to reverse link. Yeah. So this was the block diagram, what I was showing and discussing, right? So as I said, the enhancement in the performance, okay, is obtained from the direct sequence spread spectrum signal through the processing gain and as well as the coding gain that can enable the many direct sequence spread spectrum signals to simultaneously occupy the same channel bandwidth, provided that each signal has its own distinct pseudo-random sequence, right? So with that, I said what is the CDMA concept, right? We have discussed that. So the direct sequence CDMA has been adopted as one of the multiple access method for digital cellular voice communication in North America. And this is the first generation digital cellular CDMA communication system, which was developed by Qualcomm, and it has been standardized and designated as IS-95. IS stands for Interim Standard. Okay, so IS-95 by the Telecommunications Industry Association. In short, we call that as TIA, for use in the two spectrums or two frequency bands. One is 800 megahertz and second one is 1900 megahertz. Okay, so a major advantage of CDMA over any other multiple access method is that the entire frequency band is available at each base station. That is, what I can say is the frequency reuse factor, which we denote it by a letter N, which is equal to 1, we say. Okay, so the frequency reuse factor will be 1. Means every base station, in every cell, we use the same frequency. So the users are differentiated by the use of unique pseudo-noise code. Okay. So the bandwidth used for transmission from each base station to the mobile user, that we call it as a forward link. Like forward link, I said it is of 1.25 megahertz, and a separate channel with a bandwidth of 1.25 megahertz is used for signal transmission from the mobile receivers to the base station. So that we call as a reverse link, right? So signals transmitted in both the forward and the reverse links are direct sequence spread spectrum signals, and they have a chip rate of 1.2288 into 10 power 6 chips per second. Okay, so that is 1.2288 mega chips per second. Yeah, I was telling about this forward link, right? What I said at the beginning, the voice has been converted into means this speech is converted into the digital signal by using a vocoder known as the code excited linear predictive coder. So that is CELP coder. So that can provide a variable data rate starting from 9600 bits per second to 1206 bits per second. That in short we say 9.6 kbps, 4.8 kbps, 2.4 kbps, and 1.2 kbps. So this variable data rate has been passed through convolutional encoder with a coding rate of 1 by 2, which is having a constraint length, which we denote it by a letter capital L, which is equal to 9, right? So with that means when the data rates are of 4800 or 2400 and 1200 bits per second, since the coding rate is 1 by 2, right? So it will be multiplied by 2 to 4800, so we get a 9.6 kbps, right? And this 2400 will be multiplied by 4 to get a 9600 bps. Similarly, the 1200 bps will be multiplied by 8 times to get a data rate of 9.6 kbps, so which is the constant. And the output of this convolutional encoder will be of 9.2 kbps because of the coding rate of 1 by 2, right? And I said for each user there will be a pseudocode, right? So that is why is known as here mask for user I. In general, I can take any value, right? So this long code generator will be having a sequence length which is equal to what? 2 power 42 minus 1, right? So that will be able to generate 1.2288 megachips per second. Then that will be passed through decimator. Okay, so that can give a data rate of 9.2 kilo symbols per second. And as I said here, output of the convolutional encoder is passed through a block interleaver. So this block interleaver, the purpose is to minimize the effects of burst error. Okay. Then output of these two will be scrambled by a scrambler. Then, as I said, there will be wash codes. I said the length of the wash code is of 64 bit. Out of 64 wash codes, the code which is having all zeros and two more sequences are used for different purposes like pilot signal and all. So other 63 wash codes are used and each wash code represents one channel. So strictly speaking, there will be 64 channels are available. Out of 64, 3 channels are used for control signaling purposes and 61 are strictly available for transmission of the data. Okay. So then, as I said, here one is shown like that, the pilot channel, right? Then it will be splitted into in-phase and quadrature phase channels, and in-phase channel is multiplied by a pseudo-noise code having a length of 2 power 15, and similarly the quadrature channel also. Then the further processing, that is a baseband filtering, then IQ modulation happens. Output of that will be our CDMA signal. Okay, so this is how what is happening at different stages. So that has been pointed out here with points. I think you can have a look about that. Okay. So just to revise what I said, the code excited linear predictive is the type of voice coder used to generate the variable data rate of 9600, 4800, 2400 and 1200 bits per second. That is based on the speech activity in the frames of 20 milliseconds. Then that data is encoded by a rate of 1 by 2 having a constant length of 9 by using a convolutional encoder. Okay, so for lower speech activity, that is at 4800, 2400 and 1200 bits per second, the output symbols from the convolutional encoder are repeated by what? For 4800, it is repeated by twice. For 2400, it is repeated 4 times. For 1200, it is repeated 8 times. So as to maintain the constant bit rate of 9600 bits per second. Okay, then I said there will be a block interleaver which is used to overcome the effects of burst errors that may occur during the transmission through the channel. After that, the scrambling is done, which is used for data encryption to make call more secure. Okay, that is the purpose of scrambler. So the scrambler will randomize the data and prevents the transition of long series of ones and zeros. The block interleaver data rate will be of 19.2 kbps, which are scrambled by multiplication with the long code, having a chip rate of 1.2288 megachips per second, and is decimated by a factor of 64 to get a chip rate of 19.2 kilochips per second. Right? So I think the long code is used to identify the call of the mobile station on the forward and reverse link. This Hadamard or wash code, what we use, having a sequence of length 64, is assigned to each channel. Right? The 64 orthogonal sequences are assigned to each base station. One channel is used to transmit the pilot signal, which is used to measure the channel characteristics and the carrier phase offset. Another channel is used to provide the time synchronization, one channel for phasing activity. So that is why I said 3 channels is used for other purposes. Remaining 61 are used by the users. So here I said long code sequence provide a data rate of 1.2288 MCPS that has been decimated by 64 to get a symbol rate of 19.2 kilosymbols per second. So here also 19.2 kbps. So those two are scrambled. So I said the purpose of scrambling to provide more security for the call, right? Then each user data is multiplied by this Hadamard sequence. The resulting sequence will be spread by 2 PN sequences, that is in phase and quadrature phase, I said, right? Then different base stations are identified different offsets of these PN sequences. So the signals for all the 64 channels are transmitted synchronously so that in the absence of channel multipath distortion, other signals received at any mobile receiver will not interfere because of the orthogonality of these Hadamard sequences. Yeah, just it is an example which is shown how the convolutional coding is done. Right, so these are the possible rates: 9.6, 4.8, 2.4, 1.2 kbps passed through D0 to D8, means we have 9 shift registers. So output of some respective shift registers have been XORed. That is the modulo 2 operation is done, and with that, this is what the octal code what we are getting at the output of each XOR. So that we say as G0 and G1. Yeah, so this is all about the forward link. Similarly, the reverse link, that is from what your mobile station to the base station, right? So what is the process happens? So similarly, I think first thing is same. So variable data rate of 9.6, 4.8, 2.4, and 1.2 kbps is given to the convolutional encoder. Here the even convolutional coding rate is also 1/2. I think here it is some mistake is there. You can have a note of that with a constraint length of L is equal to 9 here it is. Okay, in the transmitter side it is also 9. Okay. Yeah, then block interleaver. Okay. So this is what the difference is compared to the forward link. After block interleaver, there will be scrambling, right? Here there will be 64 array orthogonal modulator is there. And another difference is from the output of the long code generators, there will be no decimation. Okay. There will be no decimator. These two are the differences. Then output of that will be again segregated into in-phase and quadrature phases. And here another difference is in the in-phase path, okay, in-phase path is the same as that of the forward link, but the quadrature path is delayed by half chip delay. That is another difference. Okay. Then the rest of the things are same. This is as far as the reverse link, that is from your mobile to the base station, how data is processed. Okay, so the reverse link modulator from the mobile transmitter to the base station is different from the forward link, right? So what is the difference only is told here. The design of the modulator is that the signals transmitted from various mobile transmitters to the base station are asynchronous. Hence, there is significantly more interference among the users, right? So the mobile transmitters are battery operated, and these transmissions are power limited to minimize the interference. Okay, so here whatever I told about each block has been told, means what is the coding rate and constraint length of the convolutional coder, right? Just you can have a look about that. So as I said, to reduce the interference to other users, the time position of the transmitted code symbol repetitions is randomized. Okay. Yeah. So here the coded bitrate will be of 28.8 kbps. Then yeah, we get with 20 millisecond frame so many encoded bits, and these are block interleaved and passed to the modulator. Then the data is modulated using 64 QAM set of Hadamard sequences having a length of 64. In that, the 6-bit block data is mapped into one of the 64 Hadamard sequence. Okay, so the result is a bit rate of 64 by 6 into 28.8, which will give you 307.8 kbps at the output of the modulator. So to understand how we are saying here 307.8 kilo symbols per second, for that the answer is this here. How do we get that? 64 by 6 into 28.8 kbps. Here I get output of the block interleaver as 28.8 kilo symbols per second. Right? So that into 64 by 6, we'll get the 307.8 kbps. Then the 64 array orthogonal modulation using the same wash function in the forward link, what we have done. So here the orthogonal data modulation is done. Okay, one wash function is transmitted for 6 coded bits. So the modulated symbol rate will be 28.8 into 64 chips per 6 coded bits. With that, we get 307.8 kilo chips per second. Yeah, similar to other speech activities. So there will be a consecutive burst which are evenly spaced in time. So the signal will be spread by the output of the long code PN generator, right, which is running at 1.2288 megachips per second. And there are only 4 PN chips for every bit of the Hadamard sequence from the modulator. So the processing gain in the reverse link will be small. So the resulting this 1.2288 megachips per second binary sequence of length 2 power 15, and its rate will be of this was 1.2288 megachips per second, that is used to create the I and Q signals. Okay, then we use output of that PN, means I and phase is band pass filtered, right? Baseband filtering is done. As I said, the Q path will be delayed by half PN sequence, that is the offset, which we make with respect to the in phase. So the signal at the output of the 2 baseband filters is an offset QPSK signal. Yeah. Yeah, this is what the specification of this IS-95. Just what is the uplink frequency, what is the downlink frequency, then how many carriers are available, what is the bandwidth, what is the type of multiple access, the number of users, what is the chip rate, what is the type of speech coder, and then what is the speech rate, what is the type of interleaving. So even interleaving also varieties are there in that block interleaving is used. And for channel encoder, what is the rate and constraint length also. Okay. Then the type of modulation. And this is for the receiver. So type of receiver is either rake receiver or we say maximal ratio combining MRC. Then the sequence is element sequence, and PN sequence is this. For long code, we are using the sequence length will be 2 power 42 minus 1, and for the spreading code, it will be 2 power 15. So these are the system parameters of IS-95. Means if you have these things in mind, then we'll be able to explain this block diagram by your own. Okay. So this is all about the IS-95 system. Since it is a block diagram approach, you can explain thoroughly. This is extra what I've given, okay, just to get a glimpse of a conventional encoder. You don't have to write this diagram. Just if you write the block diagram is more than enough. By mentioning proper bitrate at output of each block, that is important. Yes, so far, are you able to see this PPT? I don't know. Hello? Hello? So nobody is talking. Yes, everybody is. You people could see the PPT? Yes, let me, I completed that part. So let me take some numericals on this hopping, frequency hopping, okay? Yes, hope able to see this. Hello? Hello?
Yes, sir.
Yeah, please have a note of this. So like this, the numericals will come on this module. So we have discussed about frequency hop spread spectrum, right? Is at least any one of you, is it possible to read? Is it visible? Clarity is that? Yes, I did not get any response. Is it possible to read?
It is visible, sir.
Visible. Okay, please, all of you, have a look about that. So a PN sequence is generated using 4-stage linear feedback shift register, which is shown in the diagram here, right? And he has told what is the initial condition. See here, 4 shift registers are there, C0, C1, C2, and C3. And he has given the initial state as 1, 0, 0, 0. Output of C1 and C0 has been XORed, that is modular 2 operation is done, then is fed as input to the C3, right? So it says this sequence is used in a slow frequency hop, okay, MFSK system. The FH bar MFSK signal has the following parameters. So the number of bits per MFSK symbol is 2, okay? Then number of MFSK tones is what 2 power k, where the value of k is 2. Means we get 4 tones. Right? Then the length of PN segment per hop is 3. So the total number of frequency hops is denoted as 2 power k. So which is equal to 8 will be there, right? Total number of frequency hops. So he is asking you to determine the period of the PN sequence for one periodic length, then illustrate the variation of the frequency of FH or MFSK for one complete period of the PN sequence. Assume that the carrier hops to a new frequency after transmitting two MFSK symbols or 4 information bits. Okay. So assume binary data sequence to be this. This is your binary data. Okay. Then last one is sketch the variation of d-hopped frequency with time. So at least first 3 people can try. So period of PN sequence. So already done similar to this. I hope everybody can write the table quickly. Write this C3, C2, C1, C0. Do the XOR of C0, C1. Okay. So you will be able to show a table with 16 states. Just how much time I can expect you people to do this? 5 minutes is enough? Yes, is it possible to do it in 5 minutes? The table. It may not take 2 minutes, but I will give 5 minutes. I expect you people to present. That's the first step. Yes, hope everyone will do that. Yes, can I expect answer? At least one state can talk, no? Each people. So first initial state is what? 1 0 0 0. Yes, voluntarily can say what is the second. Yes, voluntarily I'm asking. After the first clock pulse, so what is the second step, second sequence? After 1 triple 0. See, output sequence will be what? For the first clock pulse, I get output sequence bit as 0, right? What is the next one? So 0 XOR with 0 is 0 only, no? So that will be fed as input to C3. Yes or no?
Yes, sir.
Yeah. So 0 XOR with 0 is 0. That will be fed as input to C3. Then 1 will be shifted to C2. Whatever there in C2 0, that will be shifted to C1. Whatever there in C1, that will be shifted to C0. and whatever there in C0, that will be shifted as output, right? So second bit is 0. Now for the third step, again still it is 0, right? C1 and C0 both are 0. So that 0 will be fed to the C3, right? Then whatever there in C3, earlier it was 0, that will be shifted to C2. Okay, in C2, 1 was there, that will be shifted to C1. In C1, 0 was there, that will be shifted to C0. In C0, 0 was there, that will be shifted as output. Okay, so Abhishek Reddy.
Sir.
Yeah, can you tell me the sequence of second step, man? See, initial state is 1,000, right?
Yes, sir.
1,000. In that, I said output bit will be 0. What is the second sequence? Means the second state.
So 0 1
Ah,
0
yeah, 0, 1, 0. Output bit will be
0.
0. Very good, man. Yes, thank you. Similarly, who is there next? What about Gaurav?
Yes, sir.
Yeah, what is the third step, man?
So 0010 output bit is
0010. Output bit will be
0.
0. Very good, man. Yes, similarly, next, Aditya Singh is there. Aditya Singh. Yes, Aditya Singh. No. Then who can say? Yes, any one of you. It is an open choice. What I think other people also can't say. Yes?
0001, sir.
Huh?
0001, sir.
That's the fourth step. How, man? How it can be 0001, man? See, in third step, you said it is 0010, no? Yeah, 1.
001.
Yeah,
Yeah,
1001. Output bit will be
1.
1. Very good. Yeah, next bit, next sequence. Yeah, other
1,
people can.
1, 0,
Yeah, 1100. Output bit will be 0.
0.
Next bit is
0110.
yeah 0110. Output will be 0.
0.
Next is
0
1011.
1011. Output bit will be 1. Right. Next is yeah next bit
0101.
yeah 0101. Output bit will be 1.
1.
Next is yes next bit
1010.
yes 1010. Output bit will be 0. The next is
1101.
1101. Very good. So output bit will be 1. Right. Next bit is
1110.
1110. Output bit will be 1. Yes. Next is
1111.
yeah 4 ones. Okay. Then next is 0111. Right.
1111.
Yeah. Next is
0
0011. Right.
Yes,
Next is
0001.
yes 0001. Next is
1000.
so 1000 means it is started repeating, right?
Yes, sir.
because our initial state was 1000. So we can stop at 0001, right? So what I can say, the output sequence will be 000, 100, 11, 01, 0, 4 ones. Is that fine? I repeat once again, my PN sequence will be what I said, 000, 100, 11, 01, 0, 4 ones. Yes, everybody has got this? Yes, no answer. I repeat once again,
Yes,
the
sir.
PN sequence will be what? 000, 100, 11, 01, 0, 4 ones.
Yes, sir.
Yeah. So after getting that, so first thing is done. What is the period of the PN sequence? We can say it is 2 power 14 minus 1, right? 2 power 4 minus 1, right? So 2 power 4 is 16, minus 1 is 15. So PN sequence length is, period of the PN sequence is 15, right? Yeah, then PN sequence for one period length. So is that one. Okay. What is that? I already told that what is the PN sequence for one period length. 000, 100, 11, 01, 0, 4 ones I said. Then next is asking illustrate the variation of the frequency of FH bar MFSK signal for one complete period of the PN sequence. Assume that the carrier hops to a new frequency after transmitting two MFSK symbols. Okay, or he says 4 information bits. Assume binary data sequence to be of what? 1, 3 zeros, 11, 01, 000. Then how many ones are there? 4 ones, 001. So this is your information sequence, information bit, right? And here MFSK, right? 2 bits is one symbol. So hopping will be what? For every 2 MFSK symbols, there will be one hop. Yeah, is it possible to illustrate this? Oh, people are doing it. So 2 bits, first you write this information bit or information sequence as 100, 11, 01, 000, then 6 ones, 001, and mark 2 bit is one symbol, one MFSK symbol. And here in the problem he has given the length of PN segment per hop will be what? 3. So total number of frequency hops 2 power k will be 8. Means 3 bit is the hopping frequency. Okay, that is you can start from FC1 to FC7. And here 2 bit is one symbol, right? So you can denote as 00, 01, 10, and 11 as either F0, F1, F2, F3. So what I wanted to say is this one. Hope able to see this. So bits of MFSK symbol. Okay, 00, I'm denoting it as FSK, MFSK tone as F0, 01 F1, 10 F2, 11 as F3. And my PN sequence. So 000 to 111 can say FC0 to FC7. Okay. So this is how the diagram which you are supposed to illustrate. So the given information is there is 1 3 zeros, right? Hope, yeah. So input binary data has been marked into 2 bits, right? For 2 MFSK symbols, there will be 1 PN sequence. So this is also taken randomly. Here FC0, and this is FC4, FC6, FC5, and this is FC7. So here it is shown, since it is 1 0, means I said 0 0 is F0, 0 1 is F1, F2, right? So I can write this as FC0 plus F2, shown here, FC0 plus F2. Next one is FC0 plus F0. So FC0 plus F0. Okay. So this will be your hopping rate, and this will be your bit rate, and this is your symbol rate. Hope we're able to make the difference, bit rate, symbol rate, and hopping rate. Okay. Yes, for the next MFSK symbol, the hopping frequency is what? It is FC4, right? So that is why it is at this point, FC4. And then this is 1 1, means it is F3. So FC4 plus F3, and F01. So FC4 plus F1. Okay. Our next one, the hopping frequency is F6. So that is why it is written FC6. Then this is 0 0. So it is F0. Then FC6, next is 0 1. So FC6 plus F1. Okay. So next one, hopping frequency is FC5. And MFSK symbol is F3. So that is why FC5 plus F3. So two symbols are of 1 1 only. So it is F3. That is why it is at the same line. Then is hopping frequency is FC7. And your MFSK symbol is, this is 2 and this is 1. So that is why FC7 plus F2, then FC7 plus F1 is written. Yes, hope this diagram is clear. Yes, I am asking, is this diagram is clear? Yes, nobody responds. Why? Still we have doubts? Yes, if anybody is having any doubt, you can ask. Nobody is having any doubt? Hello? Yes, hope everybody is busy with writing or what? Hello? Yes, is it done? Yes, Noreen.
Doing it, sir.
Doing okay. Yeah, better you people can write the grid structure, then it becomes easy.
Sir, can you tell how to do the the part after the PN sequence? I think the third subdivision of the question.
Which one?
The third subdivision.
This one?
Yeah.
Third. Yeah, here is in the problem only is given. length of PN segment per hop is 3 bits. Okay, so total number of frequency hops will be 8 we are getting, right?
Yes, sir.
2 power k is 8. So with that, it is written here with the 3 bits. So this is the sequence, hopping PN sequence from FC0 to FC7. Means from 3, with the 3 bits I can write this now, from 3 zeros to 3 ones. And it is named as FC0, FC1, FC2, FC3, FC4, FC5, FC6 and FC7. Okay, so these frequencies. Then for MFSK, he has told, he has given in the problem that 2 bits. See, number of bits per MFSK symbol is 2. So number of MFSK tones, okay, you will get 4. Isn't it? Because 2 bit is one symbol, no? So we can write it as 00 as F0, 01 as F1, 10 as F2, and 11 as F3. So these are the 4 different frequencies which I am going to modulate this data 00 by F0, 01 by F1, 10 by F2, 11 by F3. Okay, and he has given what is the input data here: 1 0 0 1 1 0 1 0 0, then 6 ones 0 0 1. This is my input binary data. Okay, so I need to make a group of 2 bits as one symbol here. Okay, so that is what is done here. Yeah, it is written that input binary data with the 2 bits as one symbol. Okay, so each symbol, what he has given here, length of PN segment, no?
Got it, sir.
Hop. Yeah?
Got it from the
Yeah.
sketching pattern.
Yeah, and this is taken it randomly. FC0, FC4, FC6, FC5, FC7 is taken randomly.
So not necessary we should take the PN sequence which we found out.
Not in order, need not be in order. And even frankly speaking, nobody is asking. I said for PN sequence, we don't take the initial state as 0, 0, 0. Right?
Yes.
For generating PN sequence, if all 3 bits are 0, 0, 0, then it will be in 0, 0 only. But here with the 3 bits, we have started writing from 3 zeros to 3 ones. And we have named it as FC0 to FC7. So among available 8 hopping frequencies, hopping carrier frequencies, we have taken it randomly. Here, it is not specified that so-and-so hopping frequencies can be taken. So out of 8, so it is taken it randomly. Okay?
Okay, sir, got it.
Yeah, hope this point is clear. It is a randomly taken. Yeah, other people can take any other random hopping frequencies among these 8 frequencies. Need not be FC0, it can be FC1 also, or FC2 also, or FC3 also, like that. So this de-hopping is about, again, demodulation. Okay. Yes, what about others? Others are doing Sachin.
Yes, sir. Doing so.
Yeah. Anand, Ananta. Yes, Ananta. Ananta is not here. Yes, man. Anand.
Sir, Ananta mic is not working with him, sir. He texted me.
ಅನಂತನ ಮೈಕ್ ಸರಿ ಇಲ್ಲ ಅಂತ ಹೇಳಿ ಮನುಷ್ಯನಿಗೆ ಹೆಂಗ್ ಗೊತ್ತಾಯ್ತಾ ಮನುಷ್ಯ
Sir,
ಮೆಸೇಜ್ ಮಾಡಿದ್ದೆ
WhatsApp
ನನಗೆ
message ಹಾಕಿದೆ ಸರ್. WhatsApp ಅಲ್ಲಿ ಮೆಸೇಜ್ ಹಾಕಿದೆ ಸರ್.
ಹೌದಾ Yes, Manish, are you doing it? Manish.
Yes, sir. Yes.
Uh, Girish, Chandrika. No, Chandrika. What about Chandan?
Sir.
Are you solving, man?
Sir.
How come today Anas has come? Mohammed Anas? But today
Yes,
is
sir.
Friday. How come you are attending today class, man? After long period.
Yes, sir. I should attend all the classes from now on.
What, man? Almost semester is going to end. You know how many classes you have attended so far?
Yes, sir.
Why you have taken so long leave?
So I had some issues, sir.
We have some issues. But you never discussed it with your proctor. What issues and all?
So I should talk to her, sir.
Okay. Yes, Pooja. What about Arshata? Arshata. Yes, Arshata. Yes, hope it is done. Shall I take the next one? One more problem. I think you can practice this also. So this is about fast FSK. Okay, the previous one was about slow frequency hop spread spectrum. This one is fast FHSK system. Just have a note of this. Yes, he has mentioned here number of hops per MFSK symbol is 2. Means one per symbol there will be 2 hops. Okay. So hopping rate will be more than the symbol rate. That is why it is called as a fast frequency hop spectrum system. Yes, he has given the PN sequence length is 15, and you need to determine the relationship between bit rate and the chip rate. Then you need to sketch the transmitted signal with time by assuming the data sequence is this 011, 01100, and one period of PN sequence. He has mentioned that PN sequence. What is that? 4 ones, 000, 100, 11010. Then a de-opted MFSK signal also. So you only given what is the PN sequence. So you don't have to generate PN sequence. Okay, so in the previous problem, he has given that PN sequence diagram. Right, from this you need to generate what is the PN sequence by considering the initial state as 1000. But in this problem, he has given directly what is the PN sequence. So you need to do the further work. Okay. So I think looking at this diagram, we'll be able to. So hope you are able to understand this. For one symbol, that is 0, 1, which is MFSK tone as F1, right, will be transmitted with two hops. One hopping frequency is FC7 and another hopping frequency is FC4. That is why one is written here FC7 plus F1 and another one is FC4 plus F1. Okay. So your MFSK symbol is 0, 1. That will be transmitted with two hops. And those two hopping frequencies are different, right? One is FC7 and another is FC4. And next MFSK symbol is 1, 0. So that will be denoted with frequency F2. For that, hopping frequencies are what? FC2 and FC3. So FC2 is this FC2 plus F2, and next one is FC3 plus F2. And next MFSK symbol is F3. So that will be transmitted with two hopping frequencies. One is FC2 and another one is FC7. So that is why here it is written FC2 plus F3. Another one is FC7 plus F3. So here it is written FC7 plus F3. And the last one is F0. MFSK symbol is F0 because it is 0, 0. And for that, the hopping frequencies are FC4 and FC2. So that is why it is written here FC4 plus F0. Another one is FC2 plus F0. Okay. So there will be multiple hops per symbol. That's one symbol will be transmitted with multiple hopping frequencies. That is why it is called fast frequency hopping. So I hope with this numericals, definitely there will be one or two numericals on this. Okay, in addition to this, I told earlier classes also what are the numericals they may ask, simple one. So just have a look about those numericals, try to practice it.